Hi everyone, thanks for watching another video. Today we'll discuss circuit elements. These are just all the components that you will find in a circuit. The first element is a resistor. All it does is absorb and then dissipate energy. For example 1, what are some examples of resistors? The first 3 examples are the clearest examples because a piece of wire, a light bulb, and a heater all gets hot, so clearly they are dissipating energy. In the fourth example, we discuss pretty much every other type of load. For every other item, such as a laptop, television, motors, cell phones, and more, they are not purely resistive loads, but they have resistive parts. And the last example are actual resistors that you can buy from the electronics store. So let's go over some key ideas. Key idea 1. Resistors can only absorb and then dissipate energy. The energy dissipated will be in the form of heat or light. The best example will be a space heater, because the heating elements get really hot and bright, so they're dissipating both heat and light energy. Key idea 2. Resistors cannot send energy to other elements. For example, you could never use a light bulb as a battery source. Okay, so why is that? The reason is that resistors do not have a way to store energy. Later, you will learn about elements that can store energy. For example, capacitors are elements that can store energy in electric fields. Inductors are elements that are able to store energy in the form of a magnetic field. That means that in certain conditions, capacitors and inductors can actually send energy back to other elements. The equation that governs the operation of a resistor is known as Ohm's law. This law says that the voltage across a resistor is equal to the current through the resistor multiplied by the resistance of the resistor. If you graph Ohm's law with I as the independent variable and V as a dependent variable, you will get a straight line. We see that the slope of the line is just a resistance value. Because the relationship is a straight line, we say that a resistor is a linear element. For example 2, we have a battery of 10 volts connected in parallel to a resistor of 5 ohms. What is the current I that goes through the resistor? First, if two things are connected in parallel, that simply means that they have the same voltage. That means that if the battery is 10 volts, then the voltage across the 5 ohm resistor will also be 10 volts. We can find the current I by starting with Ohm's law. We can then rearrange Ohm's law. Then we can substitute in the values for V and R. That gives us 2 amps. For example 3, we double the voltage of the battery to 20 volts. What is the current I that goes through the resistor? If we follow the same process we used in example 2, we get 4 amperes. Now look at our 2 circuit drawings. Notice that when the independent variable I is doubled from 2 amps to 4 amps, the dependent variable V also doubles from 10 volts to 20 volts. In other words, this shows that V and I are proportional. This means that a resistor follows the property of homogeneity. So now that we know how a resistor works, what is the purpose of an actual resistor like the ones that you buy at the store? The answer is that a resistor is used to control the flow of current. Here, we have a 10-volt battery in parallel with a resistor R. What happens when we vary the value of R? We see that as the R value increases, the current value decreases. This shows that a resistor is used to resist the flow of current. In the last row, you see that when the resistor is infinite, the current value is 0. The way you get an infinite resistance is to completely remove the resistor so that you have an open circuit. Usually in an open circuit, the current is 0 because the current cannot jump over the gap. However, if the gap is small enough, current can jump, and that is called an arc. In the very top row, you have the opposite situation. You have a resistance of 0, which creates a current of infinite. A resistance of 0 is called a short circuit and is represented by just a straight wire. However, in real life, the current is not actually infinite. It is less than that for 2 reasons. The first reason is that the battery does not supply an infinite amount of electrons. The second reason is that the wire itself possesses some small amount of resistance. This means that if you truly want to know the resistance of your circuit, you have to know how to calculate the resistance of a simple wire. The resistance of a wire is given by this formula. Rho is the resistivity of the wire material, L is the length of the wire, and A is the cross-sectional area of the wire, which is usually a circle, but it does not have to be. For example 4, you are given a copper wire with the following length, cross-sectional area, and resistivity value. What is its resistance? To solve this, we start with the formula shown above. Then we enter the values for rho, L, and A. Doing a little arithmetic, we get 0.0017 ohms. Now let's try to calculate the power absorbed by a resistor. Previously, we learned that power is equal to current times voltage. But we know that for a resistor, voltage is equal to current times resistance. Substituting this formula into P equals IV gives us a second formula for power. However, you could take V equals IR and solve for I. Now substituting this expression into P equals IV gives us a third formula for power. There is more to learn about resistors, but we will stop here and cover the other information in later videos. The next circuit element we will discuss are independent sources. An independent source is just a source whose value is independent of any other element. One example would be your typical voltage source. Here I have drawn a 9-volt battery. This source is independent because its voltage is 9 regardless of what it is connected to. Although I have used a lot of constant voltage sources in my examples, there are also time-varying voltage sources. One example is the 120-volt sine wave from your wall outlet. Another example is the voltage from a voltage waveform generator device. Both of these examples are independent sources because their value does not change based on what loads they are connected to. Another example of an independent source is a current source. A current source is a device that fixes the current value. Most of you are already familiar with voltage sources like batteries, but you may not be familiar with what is a current source. A current source is actually made of a device known as a transistor, which is powered by a voltage source. Therefore, you can actually draw a voltage drop across the current source. Here are some final tidbits about independent sources. Here I have drawn a small length of wire in green. Regardless of what the wire is connected to on the left and on the right, what is the voltage drop between points A and B? The answer is 0 because the voltage along a length of wire is the same. So the difference in voltage between points A and B is 0. This means that a wire acts as an independent voltage source of a constant value 0. Now for the drawing on the right, I have shown that at the end of some part of a circuit, we have an open circuit. Due to the open circuit, the current flow is 0 as shown. This means that an open circuit acts as an independent current source of constant value 0. Both in my discussion of resistors and independent sources, I've talked about short circuits and open circuits. So here I want to discuss what are some practical examples of both of them. In the circuit on the screen, we have a 10-volt battery in parallel with a 5 ohm resistor. If you were to measure the current in the circuit, you should read 2 amperes. If you were to measure the voltage across the 5 ohm resistor, you should read 10 volts. Let's measure the voltage first. To measure the voltage, you use a device known as a voltmeter. The voltmeter has 2 prongs. One prong you tap to the top of the resistor, and the other prong you tap to the bottom of the resistor. Using the voltmeter in this way, the voltmeter will read 10 volts. This means that the voltmeter did not disturb the voltage across the 5 ohm resistor. Okay, so how was a voltmeter able to read the voltage without disturbing it? The answer is that from the circuit's point of view, the voltmeter looks like an open circuit. This means that the black wire just looks like a dangling black wire and the red wire just looks like a dangling red wire. Dangling wires have no effect on a circuit because you cannot have a current flowing on a dangling wire because it's not a closed loop, and you cannot have a voltage drop anywhere along a wire because the voltage along a wire is the same everywhere. As a result, dangling wires can be ignored. Now we will measure the current of 2 amperes using a device called an ammeter. The ammeter also uses 2 test leads, and they must be placed next to each other on a wire. In other words, the 2 test leads cannot be separated by an element like a resistor. Here, the ammeter was able to read 2 amperes. So how was the ammeter able to do the reading without disturbing the circuit? The answer is that from the circuit's point of view, the ammeter looks like a short circuit. In this example, you see that the current, all it does is it takes a little detour to the ammeter and then it flows back into the circuit. So it is undisturbed.